A spinning disk of dust and gas holds the blueprint for an entire solar system. These protoplanetary disks are the chaotic construction sites where alien worlds are born, and what we are learning about them is rewriting the story of our own cosmic backyard. By the end of this journey, you will understand 40 of the strangest discoveries that reveal how planets truly form. We will see how newborn planets carve mysterious gaps, why these disks are chemical factories for the ingredients of life, and what bizarre forces can warp them into impossible shapes. Each discovery peels back a layer, showing a process far more dynamic and violent than anyone predicted. What do you think is the most surprising thing a planet nursery could hide? The first major clue arrived not as a planet, but as an absence. When the ALMA telescope array turned its gaze toward a young star named HL Tauri, it captured an image that stunned astronomers. There, in the dusty disk, was a series of pristine, concentric dark gaps separated by crisp, bright rings. It looked less like a chaotic cloud and more like a cosmic vinyl record, perfectly etched. This was our first direct glimpse of the architecture of a planet nursery, and it carried an immediate, shocking implication. For such clean, sculpted rings to exist, the process of planet building must begin almost immediately, within just a few million years of the star's birth. Older, slower models of planetary formation were suddenly in question. How could something so orderly emerge from the chaos so quickly? The leading theory points to an invisible force, planet-disk interaction. Picture a snowplow moving through a fresh fall. As a nascent planet, just a large core of rock and ice begins to orbit within the disk. Its gravity acts like that plow. It attracts and scatters the dust and gas in its path, clearing a clean, dark lane. Meanwhile, material piles up at the edges of this lane, creating the bright, dense rings we see. Those gaps, then, are not empty. They are the calling cards of infant worlds, carving out their territory long before they are fully grown. This single image transformed our view from speculation to observation, proving that planets do not just form in these disks, they actively and dramatically reshape them from the inside out. But those elegant gaps revealed a deeper, more troubling puzzle. If infant planets are already carving lanes in disks like HL Tauri's, then there must be enough solid material, dust and rocks, to build them. Yet when astronomers calculated the total mass of that dust in many observed disks, they came up short, dramatically short. It is a cosmic accounting error known as the missing mass problem. The math is simple and alarming. To form the core of a giant planet like Jupiter, you need a staggering amount of rocky and icy material, perhaps 10 times the mass of our entire Earth. But when you add up all the tiny dust grains visible in these young disks, the total often falls woefully short of that requirement. It is as if you walked into a lumberyard to build a mansion, but the inventory shows only enough wood for a garden shed. Where is all the building material hiding? This mass budget crisis forces a radical rethink. One possibility is that planet formation is a breathtakingly fast and efficient thief. Perhaps giant planet cores must snatch up material at a ferocious pace, consuming the available dust before it has a chance to disperse, a process that would need to start in the disk's very first million years. The other, equally compelling idea is that our observations are fooling us. Our telescopes are exquisitely tuned to see tiny, micron-sized dust grains, the fine powder floating in the disk's upper layers. But what if most of the solid mass is not in dust, but has already clumped together into larger, harder-to-see objects? Imagine trying to census a population by only counting individual grains of sand, while missing all the pebbles, rocks, and boulders. The true planetary lumberyard might be hidden in a midplane of the disk, a dense layer where pebbles the size of gravel or even larger planetesimals have already assembled, invisible to our current instruments. This missing mass isn't just a gap in our data, it's a gap in our story, hinting that the most crucial steps in planet building happen in the shadows, out of sight. This hidden midplane, if it exists, faces a terrifying and immediate threat. The very physics of the disk itself seems designed to destroy any hope of building a planet. This is the Great Radial Drift Barrier, a discovery so troubling it nearly halted the entire theory of planet formation in its tracks. Think of a pebble, perhaps the size of a grain of sand or a small bead, orbiting within the gas of the disk. It is moving at tremendous speed, but the gas around it is moving just a little bit slower due to pressure differences. The result is a constant, invisible headwind blowing against the pebble. This gas drag acts like a brake, sapping its orbital energy, and when an orbiting object loses energy, its orbit decays. It begins a slow, relentless spiral inward, doomed to fall into the central star. The calculations delivered a devastating blow. For the most promising pebble sizes, millimeter to centimeter scale, this death spiral happens not over millions of years, but over a few thousand. That is a cosmic blink of an eye. It means the very building blocks of planets should be vacuumed up by the newborn sun before they have any chance to stick together. The disk becomes a ruthless efficiency machine, not for creating worlds, but for destroying their raw materials. If this radial drift is unchecked, then planet formation should be impossible. Every pebble destined to become part of a future Earth or Jupiter would instead become stellar fuel, vanishing without a trace. This barrier presented astronomers with a profound deadline. To build a planet, you must beat the clock. You must find a way to gather those doomed pebbles into something larger, something massive enough that gas drag can no longer control its fate before they are all lost forever. The mystery of the missing mass now had a terrifying timer attached to it. The solution to this deadly countdown came from an unexpected place, not from gravity, but from pressure. Within the turbulent gas of the disk, there can be regions where the pressure peaks, creating a subtle high-pressure zone. For a pebble drifting inward, hitting this zone is like encountering a soft, cosmic wall. The gas drag that was pulling it toward the star suddenly reverses, pushing it back outward. This creates a pressure trap, a gentle eddy where drifting pebbles can accumulate, piling up in staggering densities. In these safe havens, the radial drift barrier is not just beaten, it is weaponized. The very force that was destroying planetesimals now herds them together, concentrating the building blocks by a factor of 100 or 1,000. It is here, in these ringed pressure traps, that pebbles can finally collide and stick, growing rapidly from gravel to boulders to the kilometer-sized planetesimals that are the true foundation of all planets. This discovery turned a show-stopping problem into an elegant solution. The beautiful rings we see in disks like HL Tauri might not just be the aftermath of planets, but their very nurseries, the pressure traps where the construction begins. Yet the strangeness of these disks extends far beyond their architecture, into their very chemistry. We once pictured these nurseries as sterile, frigid clouds of rock and ice. The reality is they are bustling chemical factories, brewing the complex ingredients for life in the dark and cold. In the disk surrounding a young star like TW Hydri, radio telescopes have detected a stunning inventory, simple organic molecules like formaldehyde and methanol, the kind of compounds that serve as stepping stones to greater complexity. Even more astonishing are the tentative signs of methyl isocyanate, and other prebiotic molecules, direct chemical precursors to the amino acids that form proteins. This changes everything. It means the fundamental chemistry for life does not begin on a warm, wet planet. It begins in the immense, frozen voids between the stars, on the surfaces of microscopic dust grains within these protoplanetary disks. In that profound cold, simple atoms and molecules drifting through space stick to these cosmic specks of sand. There, shielded from harsh starlight, they undergo slow, cold chemical reactions, building complexity link by link over millions of years. When these dust grains later clump together to form comets and asteroids, they become frozen time capsules, carrying this prebiotic cargo inward. The water that fills our oceans and the organic molecules that seeded our biosphere were likely delivered by these icy messengers, baked into the recipe of our planet from the very start. The nursery does not just build worlds, it pre-stocks them with the potential for life itself. Yet this elegant picture of rings and traps is not the only story these disks tell. Some planet nurseries look nothing like orderly vinyl records. They are twisted, torn, and bent into impossible shapes. The star HD 142527 hosts one of the most dramatic examples, a disk so warped it resembles a cosmic horseshoe, a vast crescent of dust curving around a central void. This is not a flat plane circling its star, it is a structure bent and broken, its inner and outer regions tilted at different, jarring angles. How does a disk, which should naturally flatten into a single smooth plane, become so contorted? The answer points to gravitational sabotage from within. An unseen companion, perhaps a small stellar partner, or a massive, still-forming planet on a wildly inclined orbit, is likely orbiting inside the gap. As this massive object plows through the disk, its gravity acts like a powerful hand, yanking and twisting the gas and dust, shearing the disk into separate, misaligned rings. The horseshoe shape itself is a colossal dust trap, a region where particles are herded and confined by the chaotic gravitational forces, piling up into a dazzling, lopsided arc of potential planet-building material. These warped disks reveal a solar system's potential for internal violence. They are the sites of gravitational tug-of-wars, where the birth of one massive object can throw the entire nursery into disarray, setting the stage for a future filled with planets on steep, tilted, and retrograde orbits, worlds that would circle their sun at bizarre angles, a legacy of the chaotic environment in which they were forged. Even as disks warp into bizarre shapes, another invisible line governs the destiny of every planet within them. Astronomers achieved a landmark feat by directly mapping this boundary for the first time, not with an image of dust, but by tracking a rare form of water. They observed the water snowline in the disk around the young star V86 Centauri. This is the critical orbital distance where the temperature finally drops enough for water vapor to condense directly into ice, frosting onto every dust grain and pebble in the region. Think of it as the cosmic frost line, a frontier that separates an inner desert from an outer frozen tundra within the planet-forming disk. Its location is not fixed. It migrates inward as the young star cools over hundreds of thousands of years, a shifting zone that fundamentally alters the building materials available at different distances. Inside the snowline, where it is too warm for water ice to exist, dust grains are dry and rocky. These particles tend to bounce off each other like tiny billiard balls, making it harder for them to stick together and grow. Beyond the snowline, however, every speck of dust is coated in a thick, sticky mantle of water ice. This icy frosting acts as a powerful glue. When these wet, frosty pebbles collide, they are far more likely to clump and merge, accelerating the growth of larger bodies. This simple physical difference, dictated by temperature and chemistry, may be the master key that unlocks the architecture of solar systems. It provides an elegant explanation for the Great Divide in our own cosmic backyard. Inside our solar system's water snowline, which likely sat between the modern orbits of Mars and Jupiter during the Sun's youth, only dry, rocky material could coalesce, leading to the formation of the smaller, denser terrestrial planets, Mercury, Venus, Earth, and Mars. Outside that line, in the deep freeze, icy pebbles could rapidly glom together into massive cores, each one growing to be 10 times the size of Earth. Once these icy cores reached a critical mass, their immense gravity could then voraciously pull in the vast reserves of surrounding hydrogen and helium gas, ballooning into the gas giants Jupiter and Saturn. The water snowline, then, is more than a temperature checkpoint. It is a cosmic assembly line that sorts raw materials, deciding which worlds will be stone and which will become giants. These pressure traps are not just theoretical safe zones, they leave behind unmistakable fingerprints. We can see their work in the intricate rings of disks like as 209, a young star system over 400 light-years away. Its disk is a masterpiece of concentric circles, a series of dark gaps and bright bands etched with startling precision. But what carves these rings? The leading suspect is the hidden hand of an infant planet. As a young world orbits within the gas, its gravity can create a disturbance, a ripple in the disk's pressure. Think of a boat moving through a calm lake. The wake it creates pushes water to the sides. Similarly, a planet's gravity can sculpt the gas around it, creating a localized high-pressure ridge ahead and behind its orbit. These ridges become the ultimate dust traps. Drifting pebbles, on their fatal spiral toward the star, pile up against these pressure walls like cosmic snow against a fence. The result is a bright, dense ring of concentrated material, a direct snapshot of a planet's gravitational influence hurting its own building blocks. In as 209, the sharpness and number of these rings suggest not one, but perhaps several unseen planets, each shepherding material in its own orbital lane, constructing their future kingdoms from the trapped dust. This transforms our view of a gap from a simple absence into a bustling construction site, where the very act of clearing a space simultaneously creates the stockpile needed to finish the job. The delicate balance of a forming solar system faces a violent and necessary release. While planets coalesce in the disk, the central star itself is undergoing a tumultuous birth, and it often vents its fury in spectacular fashion. From the poles of these infant suns erupt powerful, narrow beams of material, screaming outward at speeds of hundreds of thousands of kilometers per hour. These are protostellar jets, and the glowing shockwaves they create as they slam into interstellar space are known as Herbig-Haro objects. They look like celestial searchlights or brilliant, knotted ropes of energized gas, stretching for light years across the cosmos. For decades, they were seen as stunning but incidental fireworks, a byproduct of the star's messy formation. We now understand they are absolutely essential, acting as the system's escape valve for a fundamental cosmic property, angular momentum. As the disk feeds material onto the growing star, that material carries spin, or angular momentum, with it. If all that spin were transferred directly to the star, it would cause it to rotate so violently it would tear itself apart long before planets could form. The jets solve this. They are generated by incredibly powerful magnetic fields that thread through the star and its inner disk, acting like a twisted cosmic slingshot. This mechanism flings a small fraction of the infalling material away, not randomly, but in those two incredibly focused beams. In the process, the jets carry away the excess spin, the star's dangerous rotational energy, allowing it to continue accreting mass and growing steadily. Without these precise, high-speed outflows, stars might not be able to form at all, and the entire planet-building enterprise would never get started. But the jet's influence doesn't end there. Their intense energy can bombard the surrounding disk, potentially triggering new chemical reactions in the dust and gas, or even carving cavities that affect how and where material can accumulate. They are a reminder that a planet nursery is not a quiet, peaceful place, but a site of controlled chaos, where the violent birth of a star is intimately linked to the serene emergence of its future worlds. That violent escape of material through stellar jets is just one way a planet nursery can lose its substance. Another, more insidious process works like a slow, cosmic sandblaster, eroding entire disks from the inside out. It is called photoevaporation, and it creates a strict, inescapable deadline for any world hoping to become a gas giant. The name itself tells the story: photo for light, evaporation for turning to vapor. In this case, the intense ultraviolet radiation from the young central star, or sometimes from a massive, brilliant neighbor, acts like a cosmic blowtorch. It bombards the outer layers of the disk's gas, heating the hydrogen molecules to extreme temperatures. This superheated gas becomes so energetic it can achieve escape velocity, breaking free from the star's gravity and streaming away into space as a thin, relentless wind. Think of it as the disk slowly boiling off under an ultraviolet sun. There are two ways this erosion can happen. If the star's own ultraviolet output is strong enough, it can heat the disk's surface from the inside, creating a wind that peels the gas away layer by layer, starting from the inner regions and moving outward. But the more dramatic scenario occurs in stellar nurseries like the Orion Nebula. Here, disks swirl around young stars, but they are not alone. They are bathed in the harsh, unforgiving glare of newly formed O-type stars, behemoths that burn ferociously hot and bright. These stellar giants flood the entire region with an ocean of ultraviolet radiation, attacking the disks from the outside. The effect is devastating. Observations show these disks being sculpted into teardrop shapes, with vast plumes of gas streaming off their outer edges like smoke in a strong wind. They are literally being sandblasted into nothingness. For any planet forming within such a disk, this process imposes a cruel countdown. A gas giant like Jupiter cannot form from a rocky core alone. It must rapidly pull in a massive envelope of hydrogen and helium from the surrounding disk before that gas supply disappears. Photoevaporation is constantly draining the reservoir. If a planetary core takes too long to grow large enough to start its gas accretion, it will find the pantry is already empty. It will be stranded as a bare, rocky world, a failed giant. This means the window for building a planet with a thick atmosphere may be astonishingly narrow, perhaps only a few million years. In violent neighborhoods like Orion, that window may slam shut even faster, dooming entire systems to a future of only small, rocky worlds. The fate of a planet, it seems, is written not just by the material in its cradle, but by the harshness of the stellar environment that cradle sits within. The relentless erosion of a disk sets a brutal deadline, but sometimes the entire inner workshop seems to vanish overnight. Around certain young stars, astronomers find a bizarre and telling structure known as a transition disk. Picture a cosmic donut, a wide, bright ring of dust orbiting far from the star, separated from it by a vast, dark cavity that appears almost empty. These are not the fine, multiple rings of HL Tauri, but a single, gaping hole that can stretch for distances greater than the orbit of Pluto in our own solar system. When these objects were first identified, the explanation seemed beautifully straightforward. This must be the final, mature stage of planet formation. A giant planet, or perhaps several, had fully formed in the inner disk. As it grew to immense size, its gravity would have acted like a cosmic vacuum, relentlessly clearing all the leftover gas and dust from its orbital neighborhood, leaving behind that stark, empty cavity. The transition disk, then, was a signpost, a system graduating from its chaotic nursery phase into a more settled, planetary adulthood. It was a clean and satisfying story, a before and after snapshot of solar system construction. But as our observations sharpened, the story grew messy. Some of these disks did indeed show hints of leftover gas swirling within their inner cavities, consistent with the presence of a hidden, gap-clearing planet. Others, however, presented a deeper puzzle. Their inner regions were not just cleared of large dust grains, they were eerily devoid of almost any solid material at all, down to the tiniest specks. This was strange. Even a powerful planet would leave behind a tenuous haze of fine dust, the constant debris from collisions further out. The profound emptiness in some of these cavities suggested a different, more sweeping force was at work. Could a small companion star, a brown dwarf, be orbiting within that void, its gravity so effective that it scatters every last bit of dust? Or was this the dramatic signature of that internal photoevaporation process we discussed earlier, where the star's own ultraviolet radiation had boiled away the inner disk from the inside out, creating the cavity not with gravity, but with light? The transition disk, once a simple symbol of completion, became a cosmic riddle. Its large inner hole is a fact, but its cause is a mystery with multiple suspects, forcing us to question whether we are seeing the handiwork of a planet, the influence of a stellar sibling, or the ghostly imprint of the star's own fiery youth. The grand cavities of transition disks are not the only strange shapes emerging from the dust. As telescope resolution sharpens, we are discovering a whole zoo of intricate substructures, each one a cryptic clue. Beyond the simple rings and gaps lie spectacular spirals, bright arcs, isolated clumps, and lopsided asymmetries, features that defy the orderly image of a planet nursery. One of the most breathtaking examples whirls around the star MWC 758. Its disk is not a set of circles, but a pair of magnificent, sweeping spiral arms, like a cosmic hurricane frozen in time. These are not static sculptures, they are dynamic gravitational waves, ripples moving through the disk's fabric. The leading explanation points to an unseen architect, a massive planet orbiting just inside the spiral's origin point. As this hidden world moves through the gas, its gravity tugs on the surrounding material, much like a boat creates a wake in water. This gravitational disturbance excites a wave that propagates outward, coiling into those brilliant spiral arms we can see. The exact shape, the tightness of the coil, and even the number of arms serve as a precise diagnostic tool. By modeling these spirals, astronomers can estimate the hidden planet's mass and its orbital distance, all without ever directly seeing it. These features are forensic evidence, the gravitational fingerprints of infant giants. Other disks show different imprints, like bright, isolated clumps that could be regions where dust has been trapped by a passing planet's gravity, or horseshoe-shaped arcs where material piles up in a planet's gravitational wake. Each peculiar shape, each asymmetry, is a message written in dust and gas, a way for the unseen builders to announce their presence and reveal their properties long before they are fully formed. These cosmic fingerprints reveal a dynamic process, but one we assumed was fleeting. For decades, the textbook timeline was simple and strict: a protoplanetary disk, that swirling reservoir of gas and dust, was thought to be a short-lived phenomenon. The intense radiation from the newborn star, along with the planet-forming process itself, should drain and dissipate the entire structure in a mere 3 to 5 million years. This brief window was the rule we derived from studying our own solar system's ancient history, and it set a frantic pace for the birth of giants. But nature, it seems, loves an exception. Recent observations have uncovered a strange and wonderful class of objects nicknamed Peter Pan disks. These are not the vibrant, thick disks around infant stars, but older, quieter structures that stubbornly refuse to grow up. Take the system WISE 0806, for instance. Here, a small, dim red dwarf star, much cooler and less massive than our Sun, is encircled by a significant ring of gas and dust. The astonishing part is the star's age. While most stars have lost their disks by age 5 million years, WISE 0806 is a staggering 45 million years old. Its primordial disk has persisted for nearly 10 times longer than the standard model allowed. This is not a fading remnant, but a still, potent planet nursery that has defied the clock. How is this possible? The answer may lie in the star's gentle nature. Red dwarfs are far cooler and emit much less of the harsh ultraviolet radiation that drives photoevaporation, that slow boiling away of disk material. In this calm, low-energy environment, the destructive processes that clear away disks around Sun-like stars may operate at a glacial pace, or not at all. The implications of these long-lived disks are profound. They shatter the universal deadline for gas giant formation. If a disk can retain its gaseous fuel for tens of millions of years, then the core of a potential Jupiter has a vastly extended period to grow and begin its runaway accretion. A world that might have been a failed, rocky core in a short-lived disk could, in this patient environment, slowly and steadily pull in a massive atmosphere. Even more intriguing is the possibility of multiple generations of planet formation. In a typical disk, the first wave of planetesimals forms quickly, consuming the available pebbles and dust. But if fresh material remains in a gaseous state for tens of millions of years, it could slowly cool and condense into new generations of icy grains, providing a second or even third round of building blocks. This could lead to solar systems with a much wider variety of planetary ages and compositions orbiting the same star, a layered history of construction that our own solar system, with its presumably rapid formation, might not possess. The discovery of Peter Pan disks forces a humbling realization. The timeline we pieced together from our one example, our own solar system, may not be the universal rule. It might simply be one story, shaped by our Sun's particular brightness and temperament, in a galaxy filled with slower, more patient narratives of creation. Our own solar system's single sun is not the galactic standard. Most stars are born in pairs or even triplets, and when that happens, the planet nursery must contend with not one, but two central gravitational masters. This creates disks of astonishing and complex geometry. In some systems, like the famous Kepler-16, a pair of stars orbit each other closely, and a vast disk of gas and dust encircles them both. This is a circumbinary disk, a cosmic carousel spinning around the entire dancing stellar duo. Any planet forming within it would have two suns in its sky, a real-world Tatooine. But building a stable world, there is a gravitational tightrope act. The stars' mutual orbit creates a chaotic environment, their combined gravity churning the disk, stirring up the material and creating regions of instability. To survive, a forming planet must orbit far enough out to avoid being violently tugged by one star or the other, likely in the disk's colder, outer regions. Other binary systems present a different challenge. Here, each star can possess its own, smaller disk, a private reservoir of material orbiting just one member of the pair. These are called circumstellar disks, and they face a harsher limitation: truncation. The gravity of the companion star acts like a cosmic gardener with shears, snipping off the outer edge of the disk. It robs the disk of its most distant, voluminous material, severely limiting its total mass and physical size. A planet forming in such a cramped, truncated disk has access to only a fraction of the building blocks available in a disk around a single star. This makes the birth of gas giants exceedingly difficult, as there simply may not be enough gas within the small disk's boundaries to pull into a massive atmosphere. The gravitational tides from the companion star also inject chaos, potentially warping the disk, stirring up collisions, and flinging nascent planets into wildly eccentric, oval-shaped orbits, or even ejecting them from the system entirely. Yet, against these odds, we have found planets orbiting binary stars. Their very existence is a testament to the stubborn resilience of planet formation, a process that can carve out stable niches even in the tumultuous gravitational landscape of a double sunrise. Sometimes the most revealing view is not from above, but from the side. Drifting in the Rho Ophiuchi cloud, a stellar nursery over 400 light-years away, is a young star with a designation as poetic as its appearance: 2 Mass J16228-1370-243139-1. From our vantage point, its protoplanetary disk is presented to us perfectly edge-on, a razor-thin line bisecting the star's light. The result is one of the most iconic images in all of astronomy, an object instantly nicknamed the Flying Saucer. It looks exactly like its namesake, a bright, elongated oval of glowing dust with a perfectly dark, horizontal band slicing through its center. That dark lane is not empty space, it is the disk itself, seen in silhouette. The thick midplane of dust and pebbles is so dense it completely blocks the star's light, creating that stark black bar. The glowing ovals above and below are the disk's upper and lower surfaces, where starlight scatters off a haze of finer dust grains lofted high above the central plane. This accidental alignment is a gift to astronomers, a chance to dissect a planet nursery's vertical structure, layer by layer. We are not looking down on a flat painting, we are seeing its cross-section, its profile. This view reveals that disks are not razor-thin. They have thickness, they flare outward like a trumpet bell, growing taller as you move away from the star's gravitational grip. More importantly, the flying saucer shows us the great settling process in action. The heavy, millimeter-sized pebbles and rocks, the true building blocks of planets, have already sunk down into that dark, dense midplane lane under the gentle pull of the star's gravity. Meanwhile, the micron-sized dust, the fine powder, remains suspended in the upper atmosphere, catching the light. This vertical sorting is a critical step. For planetesimals to form, those pebbles need to be concentrated in a thin, dense layer where collisions are frequent and sticky. The edge-on view proves this is exactly what happens. It provides a direct snapshot of the construction site's floor plan, showing us the narrow, crowded workshop where the foundations of worlds are laid. separate from the dusty, lofted scaffolding above. The edge-on silhouette of a disk reveals its structure, but not its chemical soul. As we peer into these nurseries with instruments that can sense the faint whispers of molecules, a deeper division emerges. Some disks glow with the spectral signatures of carbon-rich molecules, compounds like C2H, a simple hydrocarbon. Others are dominated by oxygen-rich chemistry, their light telling a story of water vapor, carbon monoxide, and silicates. This is not a random variation. It is a chemical inheritance, a direct hand-me-down from the vast, cold molecular cloud that collapsed to form the star and its disk in the first place. If a particular region of that interstellar cloud was rich in carbon atoms locked up in complex organic molecules, that bounty gets funneled into the newborn disk. Conversely, if the cloud's oxygen was more readily available to form water ice and rocky silicates, the disk reflects that. This primordial chemical makeup is stamped onto the entire system from day one, and it may set an unbreakable rule for every world built within it. Think of it as the cosmic pantry from which all planets must cook. A carbon-rich disk offers a bounty of carbon-bearing grains and ices, the raw ingredients for a very different kind of planet. Any rocky world forming there might be built not from silicon and oxygen like Earth, but from carbides, compounds of carbon and metal. Its geology could be alien, its surface potentially covered in tar-like substances or even graphite and diamond. More crucially, its atmosphere, if it manages to hold one, would likely be thick with methane, carbon monoxide, and other hydrocarbons, a smoggy, opaque shroud utterly unlike our own nitrogen and oxygen sky. An oxygen-rich disk, like the one that birthed our solar system, provides the familiar recipe of water ice and silicate rocks, leading to terrestrial planets with the potential for water oceans and atmospheres that could, under the right conditions, become breathable. This discovery forges a strange and profound link. The chemical character of a future planet, and thus its very potential to host life as we know it, may be decided not during its own formation, but millions of years earlier, in the anonymous, frozen depths of an interstellar cloud, long before its star even ignited. The destiny of worlds is written in elements before a single planet is born. Those brilliant jets screaming from the poles of infant stars hold secrets of their own. Look closely at their structure, and you will often see them not as smooth beams, but as strings of luminous pearls. Scattered along the length of these cosmic searchlights are bright, condensed blobs astronomers call knots. These are not random clumps of gas. They are time capsules, fossil records of the most violent tantrums a young star can throw. Each knot marks a moment in the past when the star's feeding frenzy suddenly and dramatically intensified. The star experiences what is known as an FU Orionis outburst, named for the prototype star that revealed this behavior. In a relatively short span of time, perhaps just a few months or years, the star's brightness can skyrocket, increasing by a factor of 100 or more. This is not a gentle flicker, it is a full-blown stellar eruption. During such an event, the magnetic slingshot mechanism that powers the jets goes into overdrive. Vastly more material is suddenly channeled from the inner disk and launched outward at incredible speeds. This fresh, dense pulse of ejected gas rams into the slower-moving material from earlier, quieter periods. The collision creates a brilliant shockwave, a glowing knot that gets pinned to the jet like a milepost on a highway. As the outburst subsides and the jet returns to its normal flow, another knot is left behind. A jet with a series of these blobs is therefore a timeline of stellar violence, a chronicle of episodic explosions that might recur every few hundred or thousand years. The implications for the disk, and for any planets trying to form within it, are staggering. Each of these outbursts would have flooded the entire inner solar system with a tsunami of intense radiation and heat. Temperatures in the inner disk could spike by hundreds of degrees, potentially vaporizing ices and baking rocky surfaces. For any fledgling worlds in the construction zone, it would be like enduring a periodic, searing blast from a cosmic furnace. These knots tell us that a planet's infancy is not a steady, gentle warming under a constant sun. It is a story of repeated trauma, of surviving catastrophic stellar flares that reshape the chemistry and architecture of the entire nursery in an instant. Those stellar outbursts are driven by a hidden force, one that shapes the entire disk from its very heart. Magnetic fields are the invisible architects of chaos and order within a planet nursery. We cannot see them directly, but their influence is written into the motion of every charged particle, sculpting how the disk evolves and feeds its star. Observations of young stars reveal a constant, gentle rain of material, gas, and dust, spiraling from the inner disk onto the stellar surface. This steady accretion is the star's final growth spurt, and magnetic fields are the delivery system. The star's powerful magnetic field acts like a set of rigid, invisible rails, channeling ionized gas from the inner edge of the disk directly onto the star's poles. This process not only builds the star, but also regulates the disk's inner structure, creating a cleared cavity and influencing the environment where the first rocky planets will form. Beyond this orderly channeling, magnetic fields are also the prime suspect for generating the intense turbulence that churns the disk. For decades, theorists pointed to a phenomenon with a formidable name, the magneto-rotational instability, as the universal engine of this chaos. The idea is elegant. In a disk where gas is weakly ionized, the star's magnetic field lines become frozen into the spinning gas, but the gas orbits faster closer to the star and slower farther out. This difference in speed stretches the magnetic field lines, twisting them like elastic bands. The tension in these twisted lines transfers energy, stirring the gas into a froth of turbulent motion. This magnetic turbulence was thought to be the essential source of viscosity, the internal friction that allows the disk to transport angular momentum outward so material can spiral inward to feed the star. It was the theoretical key that made the entire model of disk evolution work. Yet recent observations have delivered a startling contradiction. When astronomers measure the motion of dust grains in some disks, expecting to see the wild churning predicted by strong magneto-rotational instability, they find something else, a profound and unexpected calm. The dust settles into remarkably thin, quiet layers with very little of the predicted turbulent stirring. Some disks appear to be too quiet. This presents a major puzzle. If the magneto-rotational instability is weak or absent in large swaths of the disk, what other process is driving the accretion onto the star? How does the disk evolve? The answer may lie in a different kind of magnetic effect, or perhaps in completely non-magnetic processes like the gravitational instabilities from spiral arms we discussed earlier. The search is on for the true source of the disk's inner heartbeat, a reminder that even our best theories must bend to the quiet testimony of the dust itself. This profound calm in the disk's motion only deepens a more fundamental mystery. If the building blocks are settling so quietly, why aren't they building anything? We have watched dust grains in these nurseries perform the first step with ease, clumping together from microscopic specks into fluffy aggregates the size of sand grains, then pebbles, and even centimeter-sized balls. They grow quickly, efficiently, in the disk's first million years, but then everything seems to stop. Observations reveal a strange ceiling, a barrier at roughly the size of a marble or a small bead. Beyond this point, the growth stalls. This is the dust growth problem, and it stands as a monumental roadblock on the highway from dust to world. The pebbles themselves face two cruel fates. The first we have already met, the relentless radial drift that dooms them to spiral into the star. But even if they could beat that clock, they face a second, more intimate destruction. When these millimeter-sized pebbles collide at the moderate speeds common in the disk, they do not gently merge, they shatter, they bounce apart, or they simply crush each other back into fine powder. This is the bouncing barrier, a point where the very forces that helped tiny grains stick together weak static charges and a fluffy, fractal structure become useless. To grow larger, particles need a stronger glue, something like the water ice frosting beyond the snowline, or they need to collide so gently that fragmentation is impossible. But in a dynamically evolving disk, such perfectly soft collisions may be rare, so we are left with a cosmic conundrum. Disks are filled with pebbles, the perfect planetary precursors, yet they seem trapped in a state of arrested development, unable to take the next critical step to become mountain-sized planetesimals. How does the system break through? The answer may lie in a sudden leap, a process that bypasses gradual sticking entirely. Perhaps in a dense, quiet midplane, pebbles can become so numerous that their collective gravity causes them to spontaneously collapse in a localized avalanche, directly forming a 100-kilometer-wide object in a geological instant. Or maybe the secret is in those pressure traps we discussed earlier, where the density of pebbles becomes so extreme that collisions are inevitable and their very mass helps them hold together. The dust growth problem forces us to accept that planet formation is not a smooth, continuous assembly line. It is a story of bottlenecks and breakthroughs, where nature must find a clever loophole to escape its own physical limits. The quiet midplane where pebbles settle presents its own colorful mystery. When astronomers analyze the light from these disks, they do not just see brightness, they see a subtle fingerprint in the color of the dust's emission, a clue known as the spectral index. This measurement tells a powerful story about the size of the dust grains themselves. Think of it this way: very tiny, micron-sized grains, like fine cigarette smoke, are excellent at emitting short wavelength, bluer light. Larger grains, the size of sand or pebbles, tend to glow with longer wavelength, redder light. By mapping this color across a disk, we can effectively create a growth chart, showing where the dust is fine and where it has clumped into larger building blocks. The results are deeply puzzling. In many systems, the outer regions of the disk, far from the star's heat, often show a surprisingly blue signature. This indicates the dust there remains incredibly small, almost pristine, like the original dust from the molecular cloud. Meanwhile, the inner regions show the expected redder glow, signaling that grains have successfully grown to larger sizes there. This is a complete reversal of intuition. We would expect growth to happen everywhere, but especially in the cold, calm outer disk, where sticky ice coatings should make clumping easy. The persistence of this blue dust in the far suburbs is a paradox. It means something is actively working against growth in those vast, distant reaches. One compelling explanation is a constant, violent replenishment. Perhaps in the outer disk, larger pebbles and planetesimals are colliding and fragmenting. grinding each other back down into fine powder in an endless cycle of construction and destruction. This cosmic sandblasting would constantly seed the region with fresh, blue-emitting tiny grains. Another possibility points to the harsh environment of space itself. Intense ultraviolet radiation from nearby massive stars, or even cosmic rays, could be breaking apart delicate icy grain mantles or preventing the gentle sticking needed for growth, keeping the dust in a perpetually infant state. This strange color divide paints a picture of a planet nursery with two very different personalities, an inner workshop where material consolidates into worlds, and an outer frontier locked in a chaotic stalemate, where the dream of growth is constantly reset by unseen, fragmenting forces. That billion-year-old chemical signature is not just a vague idea, it leaves a specific, measurable imprint in the water itself. When we analyze the water in our own solar system's comets, or even in the oceans of Earth, we find a peculiar and telling ratio. A tiny fraction of the hydrogen atoms are not normal hydrogen, but a heavier version called deuterium. This deuterium-to-hydrogen ratio acts as a cosmic barcode, a fingerprint that traces where that water has been. In the frigid vacuum of interstellar space, on the surface of dust grains within molecular clouds, chemical reactions naturally enrich water ice with higher levels of deuterium. It is a process that favors the heavier atom. When astronomers point their telescopes at protoplanetary disks, they can now measure this same deuterium barcode in the water vapor swirling there. The astonishing discovery is that the ratio matches. The deuterium enrichment found in the water of young disks is strikingly similar to that measured in comets within our own solar system and to the values seen in isolated interstellar clouds. This is a direct, forensic link, a chain of custody that stretches across time and space. It means the water molecules currently orbiting a young star, the very water that will one day ice over comets and fill alien oceans, is not manufactured fresh in the heat of the disk. It is a preserved relic, those molecules formed in the silent, cold darkness of the star's parent cloud, perhaps billions of years before the star itself ignited. They survived the violent collapse, the shock of birth, and the churning of the disk, carrying their ancient isotopic signature with them virtually unchanged. This tells us the disk is not a chemical blender that erases the past. It is more like a careful archivist. While the inner regions are heated and transformed, vast swaths of the outer disk remain cold enough to act as a deep freeze, preserving these primordial ices in their original state. The water that condenses onto pebbles beyond the snowline, the ice that will glue together the core of a future giant planet or be delivered to a rocky world like ours, is literally a billion-year-old inheritance from the interstellar medium. Every comet, every icy moon, every ocean in our galaxy may be built from molecules that are older than the stars they orbit, a profound continuity between the emptiness between the stars and the fullness of the worlds that fill it. The ancient water in these disks carries a billion-year-old signature, but the structures around young stars can create a more immediate and dramatic kind of signature, written not in chemistry, but in light and shadow. One of the most visually stunning discoveries is the cosmic shadow play. In some systems, a warp or a dramatic tilt in the inner disk acts like a colossal occulting hand, casting a vast, moving shadow across the outer reaches of the planet-forming material. We are not seeing the structure itself, but its silhouette projected onto a distant screen. The star HD 10453 provides the perfect example. Here, a small companion star orbits the primary, and its gravitational pull is yanking the innermost region of the disk into a steeply inclined plane, like a dinner plate tilted on its edge relative to the rest of the table. This warped inner disk does not orbit in the same flat plane as the outer disk. As it spins, its thickened rim periodically blocks a portion of the central starlight from reaching the outer disk. The result is a colossal, sweeping shadow that rotates around the entire system, a dark sector that moves like the beam of a cosmic lighthouse. From our distant vantage point, this creates an astonishing optical illusion. The outer disk, which is physically a continuous ring of dust, appears to have a giant, wedge-shaped gap cut out of it, a dark pie slice that completes a full rotation every few decades. This shadow is not a void, it is a projection, a telltale sign of hidden architecture. It is a powerful, indirect way to map the secret geometry of the innermost disk regions, areas so close to the blinding glare of the star that we could never hope to image them directly. By watching the shadow's movement, astronomers can deduce the tilt, the size, and even the precession, the slow wobble of that hidden inner warp. It is a reminder that in these nurseries, even the absence of light can be a brilliant messenger, revealing the gravitational dances of unseen companions and the twisted frameworks upon which solar systems are built. That cosmic shadow play reveals a hidden geometry, but the heart of the system is defined by a more fundamental flow. The young star at the center is not a passive observer, it is a hungry infant, and the disk is its feeding bottle. This process, called accretion, is the engine of stellar growth and a defining feature of the planet nursery. Material from the disk's inner edge does not simply orbit, it spirals relentlessly inward, drawn by gravity and magnetic forces, and finally crashes onto the star's surface at velocities that defy imagination. This constant, violent rain of gas and dust does not land evenly. It is channeled by the star's powerful magnetic field lines, which act like rigid rails, funneling the incoming material directly onto the star's magnetic poles. Where this superheated plasma slams into the stellar surface, it creates searingly hot spots, regions that can glow thousands of degrees hotter than the surrounding star. As the star rotates, these bright spots spin in and out of view, causing the star's overall brightness to flicker and pulse in a regular, telltale rhythm. This variability is a direct beacon, a signal that accretion is actively underway, and by studying its pattern, astronomers can measure the rate at which the star is devouring its own cradle. But this feeding is not always a gentle, steady trickle. In some systems, the flow becomes chaotic and explosive. These are accretion bursts, dramatic events where the star suddenly and violently gorges itself. For a short period, perhaps just months or years, the star's brightness can skyrocket, increasing by a factor of 100 or more as a colossal avalanche of disk material is dumped onto its surface all at once. What could trigger such a catastrophic feast? The instabilities are likely born within the disk itself. One leading idea points to a gravitational tipping point. As material accumulates in the inner disk, it can reach a density where its own gravity suddenly overcomes the supporting pressure. This triggers a localized collapse, like a snow shelf breaking free from a mountainside, sending a wave of gas and dust cascading down onto the star. Another, even more tantalizing trigger may be the handiwork of an unseen planet. A massive, young world orbiting in the inner disk could be stirring the pot with its gravity, creating shocks and instabilities that periodically disrupt the flow, releasing pent-up material in a sudden deluge. These bursts are more than just stellar tantrums. They are transformative events for the entire planetary system. The intense flash of heat and radiation from such an eruption would flood the inner disk, temporarily vaporizing ices, altering chemical bonds, and potentially sterilizing the construction zone of any delicate probiotic chemistry. For any fledgling worlds forming in that region, it would be a trial by fire, a searing blast that could strip away nascent atmospheres or bake their surfaces into glass. The accretion process, therefore, is not a serene background hum. It is the volatile heartbeat of the young system, a rhythm of steady consumption punctuated by violent, system-altering spikes that remind us the birth of a sun is an inherently chaotic and explosive affair. The volatile heartbeat of stellar accretion raises a profound question about the planet-building environment. If the inner disk is constantly churning with magnetic turbulence and violent outbursts, how can delicate pebbles ever find the peace to coalesce into something larger? One compelling answer lies in a theoretical sanctuary known as the dead zone. This is not a region of emptiness, but of profound quiet. Picture the disk's midplane, that dense, dark lane we saw in Edge on Silhouettes. Here, far from the star's intense radiation and the disk's own turbulent surface layers, conditions grow strangely serene. The key is ionization, for magnetic fields to grip the gas and drive the turbulent churning of the magneto-rotational instability. The gas needs to have a certain number of free electrons. It needs to be ionized. This ionization is provided by high-energy sources, like X-rays from the star or cosmic rays from deep space. But in the deep, shielded interior of the disk, especially at significant distances from the star, this ionizing radiation cannot penetrate. The gas becomes a neutral, dead calm sea. Without ionization, the magnetic fields slip through the gas like a knife through water, unable to get a grip. The powerful engine of turbulence simply shuts off. In this dead zone, the frantic stirring predicted by theory gives way to a deep, gravitational stillness. It becomes a region of remarkably low viscosity, where gas orbits the star in smooth, laminar flows with almost no internal friction. This is the perfect haven for planetesimal formation. Dust and pebbles, no longer buffeted by constant magnetic storms, can settle gently into an incredibly thin, dense layer at the midplane. In this concentrated sheet, collisions are not violent, shattering events, but gentle mergers. The density becomes so high that the pebble's own collective gravity can take over, allowing them to spontaneously collapse in localized avalanches directly into 100-kilometer-wide planetesimals, finally solving the bouncing barrier problem. The dead zone, then, is more than a quiet backwater. It is the hypothesized cradle of worlds, the sheltered workshop where the first solid foundations of planets can be assembled in peace, away from the chaotic weather of the broader disk. But is this theoretical sanctuary real, or just a beautiful idea? The search for observational evidence is one of the great detective stories in modern astronomy. Confirming a dead zone is tricky because, by definition, it is a region of inactivity. You cannot see calm. Instead, astronomers look for its indirect signatures, the consequences of its existence. One method is to study the thermal structure of the disk. A dead zone, with its lack of internal turbulent heating, should be noticeably colder than the magnetically active layers above and below it. By carefully mapping the temperature at different depths and distances in a disk, we might find these cold, quiet pockets. Another clue lies in the accretion process itself. If a large dead zone exists in the inner disk, it would act as a dam, blocking the smooth inward flow of material. Gas would pile up at its outer edge, creating a pressure maximum that could trigger episodic, violent accretion bursts onto the star, exactly the kind of FU Orionis outbursts we see. The presence of such bursts could therefore be a fingerprint of a hidden dead zone lurking within. Finding these calm havens would be a monumental discovery, proving that solar systems are built in zones of enforced tranquility, quiet rooms within the cosmic storm where gravity can finally do its patient work of assembly. Hubble's gaze into the heart of the Orion Nebula revealed a gallery of cosmic ghosts. Drifting in the harsh glare of massive newborn stars are dozens of small, glowing shapes, each one a protoplanetary disk caught in the act of being destroyed. Astronomers call them proplyds, and their forms are both beautiful and tragic. Some resemble comets with brilliant, curved heads and long, faint tails streaming away. Others look like delicate, glowing teardrops or ethereal smoke rings. These are not the serene, isolated nurseries we often picture. They are disks under siege. The immense ultraviolet radiation from nearby O-type stars, monsters like Thay, a 1 Orionis C, acts as a cosmic blowtorch. It bombards the gas in these disks, heating it until it glows and rips electrons from atoms, a process called ionization. This creates the luminous envelopes we see, but the violence does not stop there. The same radiation, combined with powerful stellar winds from the massive stars, is actively stripping the material away. The teardrop shape is a direct snapshot of this erosion. The head points toward the destructive star, its surface boiling off under the assault. The long tail is the debris, a stream of gas and dust being blown backward by the relentless stellar wind, like smoke from a candle in a breeze. We are not looking at a static picture, we are witnessing a real-time evaporation. For the proplyds of Orion, this is a death sentence. The disks are being photoevaporated at a staggering rate, losing mass so quickly that their potential to form gas giant planets may be cut off within a mere 100,000 years. Any planetary cores forming within must race against an impossibly short clock, likely dooming them to remain small, rocky worlds without substantial atmospheres. The haunting beauty of these images carries a profound implication for our own existence. Our solar system formed in a relatively quiet stellar neighborhood, isolated from such monstrous stellar neighbors. The proplyds show us the fate we narrowly avoided. Had our own protoplanetary disk been subjected to such a violent environment, the delicate, multi-million-year process of building Jupiter and Saturn might have been strangled in its cradle, leaving behind a very different, and perhaps lifeless, solar system. The haunting glow of those evaporating disks is a glimpse of a violent alternative history, but our own solar system's past is written in the silent, dark rocks still orbiting our sun. A remarkable link now connects the dust in these distant nurseries to the asteroids right here in our cosmic backyard. When astronomers analyze the light scattered by dust in certain protoplanetary disks, they find a specific spectral fingerprint, a particular pattern of absorbed and reflected colors. This signature does not match simple, pristine cosmic dust. Instead, it aligns almost perfectly with the light reflected by a specific class of objects in our asteroid belt, the V-type asteroids, like the mighty 4 Vesta. These are not primitive, unchanged rocks. They show clear evidence of having been heated, melted, and transformed in their deep past. Their spectra indicate a surface rich in basalt, a volcanic rock that only forms when a body becomes so hot inside that it melts, allowing heavier metals like iron and nickel to sink to the core while lighter, rocky magma rises to the surface and solidifies. This process is called differentiation, and it is the fundamental act of planetary birth, turning a bland mixture of rock and metal into a structured world with a core, a mantle, and a crust. Seeing this same differentiated signature in the dust of a young disk is astonishing. It means the tiny particles we are observing are not just simple grains. They are likely the shattered debris from colossal collisions between objects that have already undergone this profound internal transformation. We are not looking at raw ingredients, but at the wreckage of infant planets that formed and were then smashed apart. In the disk around the young star HD 172555, for instance, the dust carries this telltale basalt fingerprint. The implication is staggering. Within that swirling nursery, planetesimals the size of large asteroids or even small planets must have already formed, heated up from the radioactive decay of elements like aluminum-26, melted, differentiated, and then catastrophically collided, scattering their processed guts back into dust. This connects the distant past of our solar system directly to these active construction sites. The asteroid Vesta in our belt is a surviving protoplanet, a fossil from that era. The dust in HD 172555's disk suggests we are watching that same story play out in real time, witnessing the violent cycle of creation and destruction that forges both metallic cores and rocky crusts, the very building blocks of terrestrial worlds like our own. The basalt dust from shattered protoplanets tells us construction is violent, but the final blueprints of these systems are laid out in the empty spaces they leave behind. Those vast inner cavities in transition disks, the ones that look like cosmic donuts, hold a peculiar secret. They are not all carved to the same scale. Some inner holes are modest, spanning just a few astronomical units, a distance comparable to the gap between the Sun and the asteroid belt in our own system. Others are staggeringly large, stretching for tens of astronomical units, a void so immense it could swallow the entire orbit of Neptune with room to spare. This is not a minor variation, it is a fundamental divergence in design. Why would one young solar system clear out its inner real estate to the equivalent of Mercury's orbit, while another empties everything out to the frigid depths of the Kuiper belt? The size of that central cavity is the first draft of a solar system's architecture, and the drafts are wildly different. One compelling architect is, of course, a planet. A single, massive gas giant orbiting close to its star could carve a relatively small, clean gap. But to excavate a cavity dozens of astronomical units across, you would need something far more extreme. Perhaps a family of giant planets, a Jupiter, a Saturn, and an ice giant all orbiting in concert, working together to push material outward and maintain a vast cleared zone. Their combined gravitational influence could shepherd dust and gas to the outer edges, creating that enormous inner desert. Yet there is another, more destructive sculptor. Photoevaporation, that slow boiling away of the disk by stellar radiation, tends to work from the inside out. As the star's ultraviolet light erodes the inner disk, it creates a cavity that grows over time. The final size of that hole may depend on a race between the erosion rate and the planet formation process itself. If photoevaporation is swift and powerful, it can clear a huge inner region before any planet has a chance to form there, dooming that zone to permanent emptiness. If it is weaker, or if planet formation is exceptionally rapid, then worlds might coalesce first and begin carving their own, potentially smaller, gaps. This means the same basic process could produce holes of very different sizes, simply based on the star's temperament and the disk's initial conditions. The sheer diversity of these cavities tells us there is no universal rulebook. From their earliest stages, planetary systems are experiments in balance and timing, where the interplay between radiation, gravity, and chance creates a spectacular array of possible layouts, long before the final planets ever take their places. The race between creation and destruction now tightens into a desperate sprint, building a gas giant like Jupiter through the standard model of core accretion is not a gentle process. It is a frantic, two-stage construction project with a brutal deadline. First, a rocky and icy core must coalesce, growing to perhaps 10 times the mass of Earth. This alone is a monumental task, requiring the slow, patient accumulation of countless pebbles and planetesimals over millions of years. Only then, once this core reaches a critical threshold, can the second, spectacular phase begin: runaway gas accretion. The core's gravity becomes strong enough to violently pull in the vast surrounding envelope of hydrogen and helium from the disk, ballooning into a true giant in a relatively short time. The problem is the timeline. Core accretion models suggest this entire elegant sequence needs 5 to 10 million years to complete, yet the observational evidence we have from other young stars paints a starkly different picture. Many, perhaps most, protoplanetary disks are drained of their gaseous fuel in just 3 to 5 million years, consumed by the star or evaporated away by radiation. The math creates an impossible crisis. If the gas disappears in 3 million years, but you need 5 million years to build a Jupiter, then gas giants should be cosmic unicorns, vanishingly rare. And yet, they are not. We see them everywhere, orbiting other stars in staggering abundance. This glaring contradiction forces a radical rethink. There are only 2 escape routes from this temporal trap, and both rewrite the rules of planetary birth. The first is a shocking acceleration. What if gas giants do not form from the bottom up, but from the top down? This is the theory of gravitational instability. In this scenario, a massive, cold region of the outer disk could become so dense and so gravitationally unstable that it fragments directly, collapsing under its own weight in a mere few thousand years. Think of it not as assembling a planet brick by brick, but as pinching off a piece of the disk itself, a giant gaseous protoplanet born fully formed in a single, violent event. This would bypass the slow core accretion stage entirely, forming a giant well within the short lifespan of the gas disk. The second possibility is a profound historical revision. Perhaps our own solar system's formation was not the universal standard, but a fortunate exception. What if the disk that birthed our sun was exceptionally massive, stubbornly rich in gas, and remarkably long-lived, persisting for 8 or even 10 million years? This would have granted Jupiter's core all the time it needed to grow and then trigger its runaway growth in a leisurely fashion. In this view, our orderly system of gas giants might be a luxury model, built in a spacious, well-stocked workshop, while many other systems must build their giants in a frantic, last-minute rush or not at all. The very existence of Jupiter, then, becomes a clue. It asks us whether we are the product of a special, patient cradle, or whether nature has a secret, faster way to build behemoths that we have yet to fully witness. The very dust that will one day form the crusts of alien worlds carries a hidden thermal history. When astronomers point infrared telescopes at these disks, they are not just measuring heat, they are reading the mineralogical fingerprints of countless microscopic grains. Each type of crystal, each arrangement of atoms in a dust grain, absorbs and emits infrared light in a unique pattern, a spectral barcode that reveals its composition and its past. For decades, the expectation was straightforward. In the frigid outer regions of a disk, tens or hundreds of astronomical units from the star, temperatures hover only a few tens of degrees above absolute zero. In that profound cold, dust should remain in its primordial, amorphous state. The atoms of silicon, oxygen, magnesium, and iron should be jumbled together in a messy, glass-like structure, unchanged since they condensed in the cool atmosphere of a red giant star or the shockwave of a supernova long before this solar system was born. This is the raw, unprocessed feedstock of planet formation, but the infrared spectra told a different, more puzzling story. Mixed in with the signal from this amorphous glass, astronomers found the clear, sharp signature of crystalline silicates, minerals like forsterite, a magnesium-rich crystal that is a primary component of the gemstone peridot and of the Earth's own mantle. This is the dust equivalent of finding finished bricks in a quarry. Crystals like forsterite do not form in the cold dark. They require significant heat, upwards of 1,000 degrees Kelvin, to anneal and arrange their atoms into an orderly, repeating lattice. Their presence in the icy outer disk is a profound anomaly. It is as if you walked into a freezer and found, among the ice cubes, a batch of perfectly fired ceramic tiles. How did material that must have been cooked in a furnace end up in the deep freeze? The answer points to a disk that is not a static, layered cake, but a dynamic, churning mixer. One powerful explanation is large-scale radial mixing. Turbulent eddies or massive convective currents within the gas could act like a colossal conveyor belt. Dust grains that were briefly flash-heated in the searing inner disk, perhaps within a few stellar radii where temperatures are high enough to melt rock, could be caught in an upward draft. They might be lofted high above the disk plane, into a tenuous surface layer where they are no longer gravitationally bound to a tight orbit. From there, they could drift outward, carried by gentle pressures or stellar winds, before eventually settling back down into the cold outer regions, sprinkling their processed, crystalline grit across vast distances. This process effectively seeds the entire planetary construction site with pre-cooked materials. Another possibility is local, violent cooking. As planetesimals begin to form and collide in the outer disk, their impacts generate tremendous, fleeting heat. Shockwaves from these collisions, or from the spiral arms driven by hidden planets, could briefly raise the temperature of dust grains in a localized region high enough to trigger crystallization, flash annealing the material in situ. This means the very act of building planets might be baking the bricks needed for the next stage of construction. The implications are fascinating. If crystalline silicates are widespread in the cold outer disk, then the comets and icy bodies that form there are not made of purely primordial, amorphous stuff. They are built from a mixture of raw and processed ingredients. When such a comet later plunges into the inner system, delivering water and organics to a young rocky planet, it is not just bringing ice. It is delivering minerals that were forged in the inner furnace of the infant solar system and then shipped across light hours of space. The dust in these nurseries, therefore, is not a passive ingredient. Its mineralogy is a travel log, a record of epic journeys between the hot and cold extremes of the protoplanetary disk, proving that even before planets are born, the disk is a place of constant, surprising exchange. Those crystalline minerals are travelers, carried between extremes by the disk's hidden currents, but there is another, more pervasive flow that governs the entire system's fate. Alongside the spectacular, narrow jets screaming from the stellar poles, astronomers have detected a subtler, more widespread exhalation. These are the disk winds, vast, gentle outflows that rise from the surface layers of the protoplanetary disk itself, flowing outward like a cosmic mist. Unlike the violent, focused jets, these winds are slow, wide, and diffuse, emanating from a much broader region. They are the disk's quiet breath, and they may be the dominant force that finally ends the era of planet formation. What drives this gentle exodus? The leading suspects are the two great sculptors we have already met, working in tandem. The first is magnetic. Just as magnetic fields can launch the stellar jets, they can also thread through the disk's upper layers. Here, where the gas is ionized by stellar radiation, these field lines can become twisted and stressed. Like a stretched spring, they can fling material upward and outward, creating a slow, magnetically driven wind that lifts gas away from the disk surface. The second driver is the relentless power of light, photoevaporation, the star's own ultraviolet radiation, or that from nearby massive stars, heats the disk's surface to extreme temperatures. This superheated gas becomes unbound, achieving escape velocity and streaming away in a thermal wind. Whether by magnetic slingshot or thermal pressure, the result is the same, a continuous, gentle bleed of material into space. This slow loss is deceptively powerful. While the disk winds carry away mass, their true importance lies in what else they carry: angular momentum. Remember, angular momentum is the spin that keeps material in orbit, and it must be removed for the disk to evolve and for planets to migrate. The fast, collimated jets handle the star's excess spin, but the disk winds are responsible for the disk's own angular momentum budget. By lifting gas from the surface and carrying it away, the winds effectively remove spin from the remaining disk material, allowing it to spiral inward more easily to feed the star or be accreted by planets. Over millions of years, this gentle bleeding is a primary cause of the disk's dissipation. It is not a dramatic explosion, but a slow, inevitable fading. Intriguingly, these winds may do more than just drain the disk, they might also sculpt it. Theoretical models suggest that photoevaporative winds, in particular, can become strong enough to open gaps in the disk from the outside in. As the wind erodes the surface layers, it can eventually cut a channel down to the midplane, creating a gap that expands over time, much like a river carving a canyon. This could explain some of the large inner cavities we see in transition disks, not as the work of a planet, but as the ghostly imprint of the disk's own breath, slowly blowing itself apart. The disk winds, therefore, are the quiet custodians of the nursery's timeline. They are the gentle force that ultimately turns out the lights, ending the construction phase and leaving behind whatever worlds managed to form in the time allotted. The quiet breath of a disk wind is a gentle sculptor, but the structures it leaves behind can be wildly uneven. Among the most striking is a cosmic horseshoe, the vast, lopsided crescent of dust orbiting the young star HD 142527. This is not a neat, symmetrical ring. It is a dazzling, one-sided arc containing enough material to build several Jupiters, while the opposite side of the disk appears almost empty. This bizarre asymmetry is a direct challenge to our most basic assumptions. For decades, models treated protoplanetary disks as smooth, axisymmetric structures, perfect circles spinning around their stars. HD 142527's lopsided glare tells us that assumption is often spectacularly wrong, but the real mystery deepens when we look beyond the dust. When astronomers mapped the distribution of gas in this same system using carbon monoxide emissions, they found something completely different. The gas was not lopsided. It formed a much more symmetric, complete ring around the star. How can the solid building blocks be piled up on one side, while the gaseous raw material flows in a smooth, even circle? This stark contrast between dust and gas is a brilliant clue, a signpost pointing directly to the hidden mechanics of planet formation. The answer lies in how these two components behave under pressure. Gas is a fluid, and it can flow smoothly around obstacles and through gradients. Dust, however, is made of solid particles, and they respond to forces in a more stubborn way. In a disk like this, a massive, long-lived vortex can form in the gas, a swirling high-pressure zone created by an instability or the gravity of a hidden planet. Think of a whirlpool in a river. The water, the gas, flows into and around the vortex in a continuous, symmetric stream. But if you toss a handful of leaves, the dust, into that same river, they will not follow the smooth flow. They will be caught in the swirling eddy, trapped at its center, and concentrated into a dense, lopsided clump. That is precisely what we see in HD 142527. The dust grains are not free-floating. They have been herded and trapped by a gigantic, invisible weather system in the disk, a pressure maximum that acts as a cosmic dustbin, collecting solid material from across a wide region. The gas, meanwhile, simply streams around this vortex, maintaining its more uniform distribution. This discovery forces a fundamental shift in perspective. A protoplanetary disk is not a uniform soup. It is a dynamic arena with distinct neighborhoods and traffic patterns for its different ingredients. The stark asymmetry of the dust is not a flaw or an accident. It is a fingerprint of an active construction zone. It shows us where the conditions are just right for planetesimals to form, in a concentrated pile of material that has beaten the radial drift barrier by finding a safe harbor. Observing such a lopsided dust trap is like finding a single, overstuffed warehouse in an otherwise empty industrial park, a clear sign that someone or something is directing all the supplies to one specific construction site. This strange separation of dust and gas forces us to reconsider the very climate of a planet nursery. We would naturally assume the heart of a disk, its dense midplane, is the warmest place, heated by the constant friction of accretion and the glow of the young star. Yet observations of certain systems reveal a baffling thermal structure, a temperature inversion. In these disks, the upper atmospheric layers, high above the midplane, are actually hotter than the deeper, denser regions below. It is as if you walked into a cave and found the air near the entrance was cool, but the ceiling high above you was searingly hot. This completely upends our intuition about how these cosmic construction sites are heated. The primary internal heat source, the viscous energy released as gas spirals inward, should indeed warm the midplane most effectively. So why is the heat seemingly floating at the top? The answer points to an external chef cooking the disk from the outside in. The intense ultraviolet radiation blazing from the newborn star does not penetrate deeply into the dense gas. Instead, it is absorbed almost entirely within a thin surface layer, a skin just a few astronomical units thick at the disk's atmosphere. Here, molecules and tiny dust grains soak up that high-energy starlight, heating up dramatically, sometimes to temperatures of several thousand degrees. This creates a hot, glowing atmospheric blanket that sits above a significantly cooler interior. The midplane below, shielded from this direct ultraviolet barrage, remains relatively frigid, its warmth coming only from the weaker, reprocessed infrared radiation that filters down from above and from its own internal accretion processes. This thermal layering has profound consequences. It dictates where different chemicals can exist. In the hot upper atmosphere, molecules are torn apart, atoms are ionized, and complex ices are vaporized. Just beneath that layer, in the steep temperature gradient, those same atoms and molecules can recombine into new and more complex forms, raining down into the cooler midplane as exotic frosts. This inversion is not just a curious temperature reading. It is the engine for a specific kind of chemistry, one that might only be possible in a disk with a star hot enough to bathe its surface in ultraviolet light. It means the very recipe for planets changes with height, with different materials condensing out of the gas at different layers, creating a vertical smorgasbord of ingredients for any world being built below. That hot, layered atmosphere is not the only source of energy penetrating the disk's depths. From the darkest voids between the stars comes a relentless, invisible rain. Cosmic rays, atomic nuclei accelerated to nearly the speed of light by distant supernovae and black holes, are constantly sleeting through the galaxy. They are the ultimate deep-penetrating radiation, and when they strike a protoplanetary disk, they do not just bounce off the surface, they punch straight through, drilling into the dense, shielded midplane that even ultraviolet light cannot reach. This changes the entire chemical and physical game. Where starlight fails, cosmic rays succeed, providing a faint but crucial source of ionization in the deepest, darkest parts of the disk. Each high-energy particle acts like a microscopic bullet, smashing into gas molecules and stripping away electrons, creating a tenuous soup of ions and free electrons even in the cold, dense regions. This subtle ionization is the hidden spark that might power the magneto-rotational instability, the engine of turbulence, in places we once thought were dead zones. Without cosmic rays, those deep midplanes could be magnetically inert and perfectly calm. With them, they might maintain a low, simmering level of magnetic activity, a background churn that gently stirs the pot and influences how dust settles and planets begin to form. But the influence of these galactic particles goes far beyond mere stirring. They are master chemists, initiating complex chains of reactions that would otherwise lie dormant in the cold dark. When a cosmic ray smashes into a common molecule like molecular hydrogen, it can create a cascade of exotic ions and radicals, highly reactive fragments that scurry off to form new and more complex molecules. This is how some of the simplest building blocks of life, like the prebiotic molecule methyl isocyanate detected in some disks, might be forged. Cosmic rays provide the energy to jumpstart chemistry in regions too cold for thermal reactions, effectively writing organic recipes in the frozen archives of the outer disk. The strangest implication, however, is that this cosmic ray flux is not constant. It is a variable ingredient, dictated by a disk's galactic address and its own star's temperament. If a massive star explodes as a supernova within a few dozen light years of a young solar system, the resulting blast wave can flood that region with a temporary but intense surge of cosmic rays. This would create a sudden, violent chemical era within the disk, a period of intense ionization and molecule building that could last for centuries. Conversely, a young star with a powerful magnetic field can generate its own stellar wind, a protective bubble that deflects the galactic cosmic ray flux, shielding its disk and creating a more chemically quiescent environment. This means two otherwise identical planet nurseries could have vastly different chemical histories based purely on their neighborhood and the mood of their central star. One might be periodically zapped by external cosmic rays, brewing a rich and complex organic soup. The other, sheltered by its star's magnetic personality, might remain in a more primitive, simpler chemical state. The destiny of prebiotic chemistry on a future world may therefore hinge on ancient stellar explosions light years away, or on the magnetic character of its infant sun, forces that decide just how rich or how sterile the planetary pantry will be. This cosmic rain of particles sets the stage for a radical new blueprint of planetary birth. The traditional story of core accretion, where planets grow slowly by colliding with other planet-sized objects, faced a critical problem. It was far too slow to build giants within the short lifetime of a gas disk. But what if the building blocks were not boulders, but a constant, drifting rain of smaller material? This is the heart of the pebble accretion model, a revolutionary idea that has reshaped our understanding of how worlds are born. Instead of relying on rare, catastrophic collisions between massive bodies, this theory proposes that planetary cores grow with astonishing efficiency by acting like cosmic vacuum cleaners. As a young protoplanet, perhaps already the size of the Moon or Mars, orbits within the disk, it does not wait for chance encounters. It actively sweeps up the countless millimeter to centimeter-sized pebbles that are perpetually drifting inward due to gas drag. The genius of the model lies in the physics of this capture. A pebble drifting toward the star does not simply hit the planet. As it approaches the planet's gravitational sphere of influence, its path is bent. The planet's gravity pulls the pebble into a curved trajectory, dramatically increasing the cross-section for capture. Think of it not as trying to catch a single bullet with a tiny net, but as standing in a gentle snowfall where every flake is gently tugged into your path. This gravitational focusing allows a planetary embryo to grow at a breakneck pace, potentially reaching the critical 10 Earth mass threshold needed to start runaway gas accretion in just a few 100,000 years. This elegantly solves the timescale crisis, explaining how gas giants can form before their gaseous fuel supply evaporates. Yet this beautifully efficient model introduces a dramatic new tension, a cosmic competition for resources. If the first planetary core to form begins efficiently hoovering up all the drifting pebbles in its orbital lane, what building materials are left for anyone else? This is the pebble isolation mass problem. As a core grows, its gravity becomes strong enough to alter the local gas pressure in the disk, creating a small dip or trench in its orbit. This pressure bump acts like a dam, stopping the inward flow of pebbles from the outer disk. The core effectively builds a moat around its castle, cutting off its own supply line. This naturally limits its growth via pebble accretion and, crucially, allows pebbles to pile up just outside this barrier. This pile-up then becomes the perfect feedstock for a second planetary core to form farther out, starting the process anew. In this way, pebble accretion provides a potential blueprint for the architecture of an entire solar system, with planets forming in sequence, each one halting the pebble flow to seed the next. But this delicate balance is fragile. If the first planet is too greedy or forms in the wrong location, it could starve the entire outer disk of solids, potentially explaining why some systems have only a single, massive inner planet and nothing else. The model paints a picture of planet formation not as a stately procession, but as a frantic, strategic race for drifting resources, where the first mover gains a colossal advantage and decides the fate of every world that might follow. That cosmic rain of particles is filtered through a thin, volatile skin at the very top of the disk itself. High above the dark, dense midplane where planets assemble, the protoplanetary disk breathes. This is not a solid surface, but a diffuse, searingly hot atmosphere, a layer where the disk meets the void. Bathed in the star's intense ultraviolet radiation, this uppermost region is a place of constant violence and transformation. Here, molecules are not just broken apart, they are shattered into their constituent atoms and then slammed back together into exotic, reactive fragments called ions and radicals. This harsh, ionized skin is the disk's own dynamic atmosphere, and it holds chemical secrets that shape everything below. Within this irradiated frontier, astronomers have identified strange molecular signposts. Using powerful radio telescopes, they detect the faint spectral lines of ions like HCO+, a simple molecule where a hydrogen, carbon, and oxygen atom are bonded, but with a missing electron giving it a positive charge. Another is N2H+, a nitrogen molecule with an extra hydrogen atom, also ionized. These are not the building blocks of life, they are the chemical smoke from a perpetual fire. Ions like HCO+ and N2H+ are destruction products. They form when more common molecules, like carbon monoxide or nitrogen gas, are blasted by ultraviolet light or struck by cosmic rays, losing an electron in the process. They are fragile and short-lived in denser environments, but in the thin, harsh upper disk atmosphere, they thrive. Their presence is a direct tracer of the intense ionization happening there. By mapping where these ions glow brightest, astronomers can literally chart the weather patterns in the disk's upper atmosphere, measuring how far the star's damaging ultraviolet light penetrates and where the cosmic ray flux is most intense. But these exotic ions are more than just atmospheric curiosities. They are the essential guides to the disk's hidden structure and its ultimate fate. Because these molecules are so sensitive to density and radiation, their abundance acts as a precise probe. For instance, N2H+ has a peculiar quirk. It is destroyed on contact with gaseous carbon monoxide. This means it can only exist in regions where the carbon monoxide has frozen out as ice onto dust grains. By tracking N2H+, astronomers can effectively map the invisible frost line for carbon monoxide, a frontier much farther out than the water snowline, revealing where the disk becomes cold enough for other crucial ices to form. Furthermore, the rate at which these ions form and recombine is tied directly to the density of the gas. By studying them, scientists can measure how much material is left in the disk at different heights and distances, providing a crucial check on the disk's mass and how quickly it is dissipating due to photoevaporation and winds. In essence, the chemistry of this thin, hot skin is a diagnostic tool, a way to take the temperature and blood pressure of the entire planet forming engine. Ultimately, the furious chemistry of this high atmosphere does not stay aloft. The products created there, including simple organic molecules and a cascade of ions, eventually rain down into the cooler, denser layers below. This chemical precipitation seeds the midplane with a specific set of ingredients. The initial conditions for a planet's own atmosphere are forged in this process. The ratio of carbon to oxygen, the abundance of noble gases, and even the availability of prebiotic compounds that might descend onto a young world's surface are all influenced by the complex reactions happening in this violent, glowing ceiling. To understand the air of an alien world, we must first understand the air of its nursery, a thin, searing layer where light tears molecules apart and writes the first chemical lines of a planetary future. The violence of the disk's atmosphere and the frantic race for pebbles point toward a deeper, unifying truth. Planet formation is not an assembly line. It is a stochastic process, a term that simply means governed by random chance and chaotic events. The path from a smooth disk of dust to a finished solar system is not a clean, linear progression. It is a messy, violent, and highly variable journey, where random encounters and catastrophic accidents can steer the entire future of a system down wildly different paths. consider the FU Orionis outbursts, those sudden, hundredfold increases in a young star's brightness. These are not scheduled events. They are likely triggered by the chaotic collapse of overdense regions in the inner disk or by the gravitational jostling of a hidden planet. A single, random outburst at a critical time could vaporize the icy pebbles in a specific orbital zone, permanently altering the available building materials and dooming that region to only form small, dry worlds. In another system, the absence of such an outburst might allow those same ices to survive, providing the sticky glue needed to rapidly build a giant planet's core. The difference between a system with a Jupiter and one without could come down to the random timing of a stellar tantrum. The collisions themselves are inherently stochastic. The final architecture of an asteroid belt or the composition of a terrestrial planet hinges on a series of last giant impacts, colossal crashes between protoplanets the size of Mars. In our own solar system, Earth's moon is the product of one such random, glancing blow. In another system, that same impact might have been a direct hit, utterly destroying both bodies and scattering their debris into a wide ring of dust. Or it might have missed entirely, leaving a system with two large, dry worlds orbiting too close for comfort. The gravitational interactions between young planets are a chaotic dance. As multiple giant cores form, their mutual pulls can fling one another into wildly eccentric orbits, slingshotting them inward toward the star or outward into the frigid darkness. This gravitational pinball can completely reshuffle a system's layout in a few thousand years. A planet destined for the cold outer reaches might be randomly tossed into a scorching close orbit, becoming a hot Jupiter. Another might be ejected entirely, doomed to wander the galaxy as a rogue, starless world. Our own solar system's calm, orderly arrangement, with small rocky worlds inside and gas giants neatly spaced outside, might be the exception, not the rule. It could be the rare, fortunate outcome where the chaotic processes cancelled each other out, or where the random events were gentle enough to allow for a stable configuration. For every system like ours, there may be 100 others with planets on steeply tilted orbits, with missing giants, or with worlds packed so close together their years are only days long. The overarching discovery from 40 strange glimpses into these nurseries is this: there is no single recipe. A protoplanetary disk provides the ingredients and the kitchen, but the meal that gets served is the result of a chaotic, improvisational cook-off, where chance collisions, random outbursts, and gravitational luck decide the final menu of worlds. That chaotic cook-off leaves its signature not just in a planet's orbit, but in its very air. We can now read those signatures light years away. When starlight filters through the puffed-up atmosphere of a distant hot Jupiter, a gas giant orbiting perilously close to its star, it carries a chemical fingerprint. Astronomers dissect that light, and within it they find precise ratios, like the balance between carbon and oxygen atoms in the alien sky. This is more than just an exotic measurement. It is a direct archaeological record, a clue to the planet's origin written in elements that have survived billions of years. That carbon-to-oxygen ratio in a planet's atmosphere did not materialize out of nothing. It is a frozen snapshot of the specific neighborhood within the protoplanetary disk where that world was assembled. Think of the disk as a cosmic gradient of ingredients. Close to the star, where temperatures are searing, carbon and oxygen can both exist as gases, but as you move outward, they begin to freeze out at different snowlines. Water ice, which carries oxygen, condenses first. Farther out, at even colder temperatures, carbon monoxide ice forms, locking away both carbon and oxygen together. The exact location where a giant planet's core forms determines which of these ices it can greedily accrete along with its rocks. If a planet core forms just inside the water snowline, it will swallow mostly rocky, oxygen-rich silicates, but very little carbon-bearing ice. When it later pulls in its massive gaseous envelope, that atmosphere will reflect this oxygen-rich foundation. Conversely, if a core forms far out, beyond the carbon monoxide snowline, it will feast on a bounty of carbon-rich ices. Its subsequent atmosphere will be steeped in carbon-bearing molecules like methane and carbon monoxide, boasting a much higher carbon-to-oxygen ratio. The atmosphere of a mature hot Jupiter, then, is a time capsule. Even though the planet may have later migrated inward to its scorching close orbit, its atmospheric chemistry remains stubbornly tied to its cold, distant birthplace. By measuring these ratios in exoplanet atmospheres today, we are effectively performing an archaeological dig. We are reconstructing the long-vanished geography of its protoplanetary disk, mapping where the frost lines fell and pinpointing the icy frontier where this giant world first took shape. Each atmosphere becomes a page from a lost construction manual, telling us not just about the planet, but about the forgotten nursery that built it. The chaotic origins of a giant planet do not end with its own birth. As a young Jupiter or Saturn greedily pulls gas from the surrounding protoplanetary disk, it creates a swirling vortex of its own. This is the circumplanetary disk, a miniature, spinning disk of gas and dust that orbits the infant giant itself. Think of it as a cosmic nesting doll, a smaller, second-generation construction site nestled within the grand architecture of the primary disk. Within these compact, turbulent rings, an entire new chapter of formation unfolds, the genesis of moons. Our own solar system holds the blueprint. The 4 large Galilean satellites orbiting Jupiter, Io, Europa, Ganymede, and Callisto are not captured asteroids. They are a coherent system, a family born together. Their orderly, circular orbits within Jupiter's equatorial plane are the definitive fingerprint of formation within a flat, rotating disk. That disk was Jupiter's own personal nursery, a circumplanetary disk that existed for perhaps only a few million years as the planet finished its gas accretion. In this intimate environment, dust grains coalesced into moonlets, which then swept up material in their own lanes, growing into the diverse worlds we see today, from the volcanic furnace of Io to the icy, ocean-hiding shell of Europa. The process mirrors planet formation on a smaller, faster scale, but with a crucial twist. The raw materials were not pristine. They were a filtered sample of what Jupiter had already consumed and processed. This means the chemistry of the Galilean moons carries a mixed history, part primordial disk, part processed through the heat and turbulence of the giant's own growth. For decades, this was a compelling theory built on the end product. Now, the hunt is on to catch these moon forges in the act. Directly imaging a circumplanetary disk is a monumental challenge. These structures are tiny on cosmic scales, perhaps only a few times the diameter of Jupiter's orbit, and they are drowned in the blinding glare of both their host star and the massive, bright planet they surround. Yet astronomers are finding clever, indirect ways to sense their presence. One promising method involves looking for specific gaps or kinematic signatures in the primary protoplanetary disk. As a forming giant planet carves its gap, the complex flow of gas around it can create a small, persistent vortex, a standing shockwave where material is funneled down onto the planet and into its own disk. Sophisticated computer models predict that this accretion process should leave a subtle fingerprint in the velocity of the gas, a specific pattern of twists and Doppler shifts that new instruments like the James Webb Space Telescope might be able to detect. Another clue comes from the system's energy budget. The process of gas crashing from the protoplanetary disk down into the circumplanetary disk releases tremendous heat. Some models suggest this could create a localized, warm glow in the infrared or millimeter wavelengths, a faint but distinct hotspot orbiting just beyond the planet's immediate atmosphere. A handful of candidate systems, like the young star AS-209, show intriguing, unresolved blobs of emission near suspected planet-carved gaps, sparking excitement that we might be seeing the first blurred portraits of these moon factories. Successfully pinning one down would be a transformative leap. It would move moon formation from a historical deduction to an observable science. We could measure the disk's mass, its temperature, its chemical composition, and its lifetime. We could watch, in real time across the galaxy, the same processes that built the icy ocean worlds in our own backyard, answering whether Europa-like moons are cosmic rarities or common jewels adorning giant planets throughout the Milky Way. The search for circumplanetary disks is the search for the final link in the chain of cosmic creation, the moment a star's nursery gives birth to a planet's own family. The destiny of a planet is not written by its star alone. It is a verdict delivered by a jury of stellar peers. Most stars, including our Sun, are not born in isolation. They emerge from the dense gas of a stellar nursery in litters, forming open clusters where hundreds or thousands of siblings shine in close proximity for millions of years. This crowded childhood is not a peaceful time in the suburbs. It is a cosmic urban environment where close encounters and harsh neighbors shape and often shatter the delicate process of planet formation. The protoplanetary disk swirling around a young star is vulnerable, a vast, thin target in this stellar metropolis. A passing star, even a distant cousin on a slightly different orbital path through the cluster, can have a catastrophic gravitational effect. As it swings by, its gravity acts like a tremendous tidal force, yanking on the outer reaches of the disk. The results are dramatic and permanent. A close flyby can shear off the disk's outer edges, truncating it, robbing a future solar system of the vast reservoir of icy material needed to build giant planets and distant comet clouds. In a more violent encounter, the passing star's pull can warp the entire disk, tilting its plane relative to the star's equator. This would leave a lasting legacy, a system where all the planets orbit at a bizarre, skewed angle, a fossil record of that ancient stellar near collision. In the most extreme cases, a direct hit from a massive sibling could strip the disk away entirely, leaving a young star barren and alone before its planets ever had a chance to form. But gravity is not the only threat in the cluster. The true danger often comes from the brightest members of the family. Within these nurseries, a few stars will be born as massive, blazing O-type or B-type behemoths. These stars burn ferociously hot and die young, but during their brief lives, they flood the entire cluster with an ocean of intense ultraviolet radiation. For any nearby star with a protoplanetary disk, this is an existential crisis. We have already seen how a star's own ultraviolet light can slowly boil away its disk from the inside. Now, imagine that external radiation multiplied 1,000-fold, bathing the disk from all sides. This is external photoevaporation, and it is a far more efficient and ruthless destroyer. The ultraviolet blast from a massive neighbor heats the entire surface of a nearby disk to extreme temperatures. The gas at the disk's outer edge, less bound by the star's gravity, is particularly vulnerable. It is superheated until it achieves escape velocity, streaming away in a vast, relentless wind. Observations in places like the Orion Nebula show these evaporating disks as glowing proplyds, their shapes sculpted by the stellar wind-like sand dunes in a hurricane. This process can drain a disk of its lifeblood, its gas, in a mere 100,000 years, a blink of an eye in planetary time. For any giant planet core trying to form, this is a death sentence. The gaseous fuel it needs to grow its massive atmosphere is ripped away before the core can even finish assembling. The result is a system forever limited to small, rocky worlds, its potential for gas giants extinguished by the glare of a brilliant sibling. This adds a profound and humbling layer of randomness to the galactic lottery of planet formation. Two stars could be born with identical masses, from identical clouds, with identical disks. But if one forms in a quiet, sparse region of a cluster, and the other forms within the deadly glare of a massive O-type star, their fates will diverge completely. One might build a system of gas giants and icy worlds over millions of peaceful years. The other might have its construction site dismantled before the foundation is even poured. Our own solar system's calm, orderly architecture may be a quiet testament to a fortunate youth. We likely formed in a relatively benign corner of our birth cluster, far enough from any monstrous stellar siblings to avoid their destructive radiation and gravitational bullying. Our disk was allowed to live out its full, multi-million-year lifespan, giving Jupiter and Saturn all the time they needed to form. The legacy of stellar siblings forces us to see planetary systems not as independent creations, but as products of their community. A star's planetary destiny is not just about the material it was born with, but about the company it kept, the gravitational traffic it endured, and the celestial weather it survived in the volatile neighborhood of its youth. The chaotic influence of stellar siblings underscores just how much we have yet to see, how many mysteries remain locked within the faint glow of these distant nurseries. Our story of 40 strange discoveries is not a conclusion, but a prologue. The next great leap in understanding is already underway, powered by a new generation of telescopes that will turn our blurry glimpses into crystal-clear portraits. The James Webb Space Telescope, with its gold-plated mirrors and suite of infrared instruments, is not merely an upgrade, it is a revolution in perspective. For decades, the inner regions of protoplanetary disks, the very zones where rocky planets like Earth are forged, have been hidden in plain sight, lost in the blinding glare of their central stars. Webb changes that. Its infrared eyes are perfectly tuned to see the warm glow of dust and the spectral fingerprints of molecules in these terrestrial planet factories. It can peer directly into the inner cavities of transition disks, not just to map the dust, but to take a complete chemical census. We will be able to trace the journey of water vapor from the cold outer disk all the way to the snowline, watching where it freezes onto grains. We will hunt for the building blocks of life, complex organic molecules, in the very places where Earth-like worlds are assembling, asking if our own chemical beginnings are a common blueprint or a rare accident. Perhaps most thrillingly, Webb may detect the thermal signatures of the youngest, hottest protoplanets themselves, massive worlds still glowing from the heat of their violent formation, their presence revealed not by a gap they carve, but by their own infant warmth against the dark backdrop of space. While Webb dissects the inner workings of disks, a colossal new eye on the ground will push the boundaries of direct vision. The extremely large telescope, rising in the Chilean desert, will gather more light than any optical telescope ever built. Its primary mirror, spanning nearly 40 meters, will provide a level of detail that borders on the surreal. The ELT's immense resolution will allow it to see not just the broad gaps in disks, but the fine structures within them. It will distinguish between a gap carved by a single planet and one sculpted by several, mapping the intricate spiral arms and vortices with precision we can now only simulate. Its primary goal in this field is audacious: to directly image a protoplanet itself, not a mature world orbiting a quiet star, but a true infant, a Jupiter-sized object still embedded in its natal disk, perhaps still accreting gas from a circumplanetary disk of its own. Seeing such an object, a point of light within a dark lane of dust, would be the ultimate confirmation of our theories, the smoking gun that closes the loop between hypothesis and observation. Beyond imaging, the ELT's powerful spectrographs will analyze the light from these disks in exquisite detail, measuring the subtle Doppler shifts in gas that reveal hidden gravitational influences, mapping winds, and tracing the flow of material with a fidelity that will make today's best maps look like rough sketches. Together, Webb and the ELT represent a fundamental shift. They move us from inferring planets from their effects to potentially seeing them in their cribs, from guessing at chemistry to taking a direct inventory of the ingredients in alien kitchens. The 40 strange discoveries we have explored are the questions written in the dust. These new telescopes are the keys that will finally let us read the answers. This cosmic archaeology leads us to the ultimate, humbling question: are we, in gazing at these swirling disks of dust and gas, simply seeing our own past? Every strange gap, every elegant spiral arm, every faint chemical signature we detect in a disk 400 light-years away is more than just data. It is a direct clue, a preserved moment from the chaotic construction of our own home. When the ALMA telescope revealed those crisp, concentric rings in HL Tauri, we were not just looking at another star's nursery. We were witnessing the probable blueprint for our own solar system's infancy, a stage our Sun and its planets passed through 4.6 billion years ago. The violent FU Orionis outbursts that bake inner disks. Our young Sun likely experienced those, their searing heat potentially vaporizing the original water in Earth's building zone, forcing it to arrive later via icy comets. The vast horseshoe of dust in HD 142527. It shows us how Jupiter's core might have trapped its own building materials, growing rapidly in a concentrated pile. The missing mass problem, the radial drift barrier, the desperate race against photoevaporation, these are not abstract puzzles. They are the very crises our solar system had to solve, and somehow did, to produce the stable, life-bearing world we stand on today. By studying this gallery of alien nurseries, we are conducting the most profound historical experiment possible. We cannot rewind time to watch our own formation, but we can observe countless other systems, each frozen at a different stage of development. One disk shows a smooth, featureless cloud, a solar system at year zero. Another shows a clean central cavity, a system perhaps 5 million years old, its inner planets nearly complete. A third shows spectacular spirals, the gravitational wake of a hidden, forming giant. By arranging these snapshots in a logical sequence, we can stitch together a movie of our own origins. This makes protoplanetary disks the most important cosmic laboratories we will ever have. They are the only places where the fundamental, physical processes of world building are actively unfolding, available for us to measure and test. Every observation refines the story, turning mythology into a precise, if still incomplete, chronicle. So the next time you look up at the night sky, remember this. The planets orbiting our sun, the very ground beneath your feet, were once nothing more than anonymous specks within a spinning disk of dust, facing the same universal laws and chaotic accidents we now witness light years away. In a very real sense, we are the children of that chaos, the unlikely survivors of a billion-year construction project whose blueprints are still being written in the light of distant, newborn stars. 40 glimpses into these cosmic cradles have revealed a universe of staggering complexity. We have journeyed from the first pristine rings of HL Tauri to the violent stellar outbursts that bake infant worlds, from the hidden chemistry brewing life's precursors to the gravitational wars that twist disks into impossible shapes. The overarching story is clear. Planet formation is not a serene, orderly assembly line. It is a dynamic, chaotic, and chemically rich drama, a billion-year construction project governed by chance encounters, desperate races against time, and the subtle interplay of light, magnetism, and gravity. Each strange discovery, from the missing mass problem to the whispering disk winds, peels back a layer of assumption, revealing a process far more wondrous and violent than we ever dreamed. These are not just curiosities about distant stars. They are the fundamental pieces of a puzzle that explains our very existence. By solving the mysteries of these protoplanetary disks, we are ultimately reading our own origin story, written in the dust of alien nurseries. It is a story that tells us we are the products of cosmic chaos, shaped by laws and accidents that are now playing out across the galaxy. So, as this journey ends, we turn the question to you. Which of these 40 discoveries shocked you the most? Was it the billion-year-old water, the lopsided dust traps, or the terrifying deadline to build a gas giant before the disk evaporates? Let us know in the comments below. If you want to dive deeper into the universe's greatest mysteries, be sure to like this video, subscribe to the channel, and hit the notification bell. Our next adventure into the cosmos is already on the horizon.